Hello, and welcome to another edition of Math, Music, and More. In the last episode, we were talking about even integers and their squares, and how when we looked at the difference functions between successive squares of even integers, we found a pattern, and that if we took the difference of the differences, the result was always 8. And in fact, we derived a simple analytical method to demonstrate that this is a pattern that would keep recurring ad infinitum. And just to refresh, so you don't have to go all the way back, we're not going to redo the analytical proof, but if we have integers that we then square, we could have 0, 2, 4, 6, and of course it's 0, 4, 16, 36. So first, step 1, take the differences. Here it's 4, here it's 12, and here it's 20. And as I mentioned a moment ago, we're taking the differences of the difference to actually see if there's a pattern. And sure enough, from 4 to 12, we have 8, and 12 to 20, we again have 8. And as I mentioned a moment ago in the prior episode, we in fact demonstrated analytically that this is something that would continue ad infinitum, this pattern. What I want to do in this video is point out that some of us sometimes have the inclination, myself included, to focus on things first analytically, when in fact, sometimes visually and geometrically, a much more clean solution emerges that even a child can understand. And I'd like to walk you through what sort of dawned on me and how we could do this actually in a visual geometric way. So let me clean some space here. And what we're going to do is just basically create squares. So let's start with n and just make a square. So we have a square with two sides n. Now keep in mind that the analytical proof did not require n to be even. So everything that we're actually talking about here applies to both successive even integers as well as successive odd integers. That difference of 8 will continue ad infinitum. And here it's the same case. We don't really care if n is even or odd, because watch what happens. If either n is even or odd, depending on what set we choose, the next member of the set will of course be something that's up 2. 1, 2. And you get something that's roughly like this, right? Let me go like this. But we need to do it again, because again, we're not just looking at a difference, we're looking at the difference of differences. And therefore we need at least 3 numbers, because we need a difference here and another difference to check the difference of the difference. So let's go ahead and do that. Let's make this go up yet again. So it becomes another 1 and another 2, and another 1 and another 2. And this is where you start to see something interesting happen. Remember how to get from this square, n squared, to this square, n plus 2 squared, you had to add this piece, the similar piece here, and also this square. All 3 of those things make up visually the difference between n squared and n plus 2 squared. Let's use those same things in the next n plus 4 squared. It would be this piece, which I'll hash differently just so we can see it, this piece, and 1 square up there. Sorry if it looks a little messy, but this piece is the same as that, this piece is the same as that, and this piece is the same as that. That corresponds to the same difference. So what is the difference of the difference? This square and this square. And this is a 2 by 2, and this is a 2 by 2. And hence, the difference of the difference equals 8. This is a very, very simple, clean, geometric, visual approach to demonstrate how, irrespective of the n that we choose, odd or even, that in fact the difference of the difference will always be 8. So I just wanted to point this out, that sometimes if you're stuck a little bit with the analytics, jump to a geometric visualization and intuitive approach, because it can sometimes work wonders. Hope you enjoyed it.